until then, I think we're gonna get started. So put in a marker in chat. All right, today we're gonna be going through Type Object of the Game Programming and Patterns book. We've been reading through all these different patterns, and this is the end of this behavioral patterns section. So, intent. Allow the flexible creation of new classes by creating a single class, each instance of which represents a different type of object. Is that sort of like a factory pattern? Motivation. Imagine we're working on a fantasy role-playing game. Our task is to write the code for the hordes of vicious monsters that seek to slay our brave hero. Monsters have a bunch of different attributes: health, attacks, graphics, sound, etc. But for example purposes, we'll just worry about the first two. So, health and attacks. Each monster in the game has a value for its current health. It starts at full, and each time the monster is wounded, it diminishes. Monsters also have an attack string. When a monster attacks our hero, the text will be shown to the user somehow. We don't care how here. The designers tell us that monsters come in a variety of different breeds, like dragon or troll. Each breed describes a kind of monster that exists in the game, and there can be multiple monsters of the same breed running around in a dungeon at the same time. The breed determines a monster's starting health. Dragons start off with more than trolls, making them harder to kill. It also determines the attack string. All monsters of the same breed attack the same way. The typical OOP answer. With that game design in mind, we fire up our text editor and start coding. According to the design, a dragon is a kind of monster, a troll is another kind, and so on with the other breeds. Thinking object-oriented, that leads us to a monster-based class. This is the so-called is-a relationship. In conventional OOP thinking, since a dragon is a monster, we model that by making dragon a subclass of monster. As we'll see, subclassing is only one way of enshrining a conceptual relationship like that into code. Okay, so we have our class monster. Right, I mean, when I say class monster, this is mostly, so it has protected here. So this can only be called from the inherited classes. Inherited? No, it's the other way around. But okay, so if I create a file here for JavaScript. So Rust doesn't really have the ability for us to do subclassing. So this isn't necessarily super good for it. But if we do type object.js, in JavaScript, we can kind of sort of do this. So this is converting C++ over. So if I just copy this straight in, this is the constructor. So this becomes constructor. Then there's going to be get attack method. That's going to essentially just be nothing right now. Protected. So there's no such thing as protected in normal JavaScript, maybe in TypeScript. But this is going to be a method named monster with a capital N. That's interesting. It takes in the starting health and then it's going to set health equals starting health. So we're going to go here like this, move you up, this dot, health, I think equals. So setting that like that. Then we're saying like, okay, we need this int health, so we can put that in a constructor actually. So this dot health equals I guess like 0 to set it to an integer at least. And then we don't need this at all. So if I do that, oh, you can automatically fix these. Okay. We've got you. Right, there's no int. We don't care about types here. This is JavaScript. All right, so that we get, so we'd have our monster base class. The public getAttack function lets the combat code get the string that should be displayed when the monster attacks the hero. So I guess what this sounds like would be, maybe by default, we would say something like return, I am attacking you, attaching you. And then you can override that to be something better. Each derived breed class will override this to provide a different message. The constructor is protected and takes the starting health for the monster. We'll have derived classes for each breed that provide their own public constructors that call this one, passing in the starting health that is appropriate for that breed. Now, let's see a couple of breed subclasses. Probably easier for me not to just copy paste that in. Okay, so we're gonna have a dragon and a troll. So let's go ahead and create a dragon. Here we have our dragon. So the constructor for dragon sets the monster to be 230. Okay, so we're gonna have constructor. We're gonna call super. And then we're gonna call this dot monster. We're gonna pass in 230 as its starting health. Then get attack. Okay, so then we're overriding get attack. And return the dragon breathes fire. All right. Then we have, oh, and I forgot, we need to extend. Extends monster. Then I can copy this, clone this again, and now we're gonna get the troll. The troll extends public monster, this up monster, so it's 48, significantly lower health. Attack, the troll clubs you. Exclamation points make everything seem more exciting. Each class derived from monster passes in the starting health and overrides get attack to return the attack string for that breed. Everything works as expected, and before long, we've got our hero running around slaying a variety of beasties. We keep slinging code, and before we know it, we got dozens of monster subclasses, from acidic slimes to zombie goats. Then, strangely, things start to bog down. Our designers ultimately want to have hundreds of breeds, and we find ourselves spending all of our time writing these little 7-line subclasses and recompiling. It gets worse. The designers want to start tuning the breeds we've already coded. Our formerly productive workday degenerates to get email from designer asking to change health of troll from 48 to 52. Check out and change troll.h. Recompile game. Check and change. Reply to email. Repeat. We spend the day frustrated because we've turned into data monkeys. Our designers are frustrated because it takes them forever to get a simple number tuned. What we need is the ability to change breed stats without having to recompile the whole game every time. Even better, we like designers to be able to create and tune breeds without any programmer intervention at all. A class or a class. At a very high level, the problem we're trying to solve... Oh, I forgot to turn off the second game. I'm sorry. Let me do that now. At a very high level, the problem we're trying to solve is pretty simple. We have a bunch of different monsters in the game, and we want to share certain attributes with them, between them. A horde of monsters are beating on the hero, and we want some of them to use the same text for their attack. We define that by saying that all of those monsters are the same breed, and that the breed determines the attack string. We decided to implement this concept using inheritance since it lines up with our intuition of classes. A dragon is a monster, and each dragon in the game is an instance of this dragon class, defining each breed as a subclass of an abstract-based monster class, and having each monster in the game be an instance of that derived breed class mirrors that. We end up with a class hierarchy like this, okay? So monster and dragon, troll, and lots more subclasses all inherit from monster. Each instance of a monster in the game will be of one of the derived monster types. The more breeds we have, the bigger the class hierarchy. That's the problem, of course. Adding new breeds means adding new code, and each breed has to be compiled in as its own type. This works, but it isn't the only option. We could also architect our code so that each monster has a breed, instead of subclassing monster for each breed. We have a single monster class and a single breed class. So basically monster, and then we have a breed which inherits from monster, but then breed can be sort of, I guess it might pull in its data from some other source. Oh, and it's a different symbol, so it's references, so breed references monster. That's it, 2 classes. Notice that there's no inheritance at all. With this system, each monster in a game is simply an instance of class monster. The breed class contains the information that's shared between all monsters of the same breed, starting health, and the attack string. To associate monsters with breeds, we give each monster instance a reference to a breed object containing the information for that breed. To get the attack string, a monster just calls a method on its breed. The breed class essentially defines a monster's type. Each breed instance is an object that represents a different conceptual type, hence the name of the pattern, type object. What's especially powerful about this pattern is that now we can define new types of things without complicating the code base at all. We've essentially lifted a portion of the type system out of the hard-coded class hierarchy into data we can define at runtime. We can create hundreds of different breeds by instantiating more instances of breed with different values. If we create breeds by initializing them from data read from some configuration file, we have the ability to define new types of monsters completely in data. So easy, a designer could do it. Which I guess is the idea, right? Like, if we're making our solo game and we're the designer and the developer, then I guess like we might fall into that trap where it's like, okay, I don't know, I'm the developer and designer, I might as well just write this the entire, write it in this way. But if we put ourselves into like, okay, I'm gonna be in designing mode today, then they don't necessarily want to be in the code. And of course, in a big AAA project, this is huge. Your designers don't necessarily code at all unless you have a technical designer. The pattern. Define a type object class and the typed object class. Each type object instance represents a different logical type. Each typed object stores a reference to the type object that describes its type. Instance-specific data is stored in the typed object instance, and data or behavior that should be shared across all instances of the same conceptual type is stored in the type object. Objects referencing the same type object will function as if they were the same type. This lets us share data and behavior across a set of similar objects, much like subclassing lets us do, but without having a fixed set of hard-coded subclasses. It's a lot of like type referencing 2 different like classes essentially. I want to see the code before I really like judge that. When to use it. This pattern is useful anytime you need to define a variety of different kinds of things, but baking the kinds into your language's type system is too rigid. In particular, it's useful when either of these is true. You don't know what types you will need up front. For example, what if our game needed to support downloading content that contained new breeds of monsters? You want to be able to modify or add new types without having to recompile or change code. Keep in mind, this pattern is about moving the definition of a type from the imperative but rigid language of code into the more flexible but less behavioral world of objects and memory. The flexibility is good, but you lose some things by hoisting your types into data. The type objects have to be tracked manually. One advantage of using something like C++'s type system is that the compiler handles all of the bookkeeping for the classes automatically. The data that defines each class is automatically compiled into the static memory segment of the executable and just works. With the type object pattern, we are now responsible for managing not only our monsters in memory, but also their types. We have to make sure all of the breed objects are instantiated and kept in memory as long as our monsters need them. Whenever we create a new monster, it's up to us to ensure that it's correctly initialized with a reference to a valid breed. We've freed ourselves from some of the limitations of the compiler, but the cost is that we have to re-implement some of what is used to be doing for us. Some of what we are used to C++ doing for the compilers. Basically, we're getting away from the type system, and because we're holding it outside of the type system, maybe like just strings or a JSON object or something like that. Under the hood, C++ virtual methods are implemented using something called a virtual function table, or just vtable. A vtable is a simple struct containing a set of function pointers, one for each virtual method in a class. There is one vtable in memory for each class. Each instance of a class has a pointer to the vtable for its class. When you call a virtual function, the code first looks up the vtable for the object and then calls its function stored in the appropriate function pointer in the table. Sound familiar? The vtable is our breed object, and the pointer to that vtable is the reference the monster holds to its breed. C++ classes are the type object pattern applied to C, handled automatically by the compiler. It's harder to define behavior for each type. With subclassing, you can override a method and do whatever you want to. Calculate values procedurally, call other code, etc. The sky is the limit. We could define a monster subclass whose attack string changed based on the phase of the moon if we wanted to. Handy for werewolves, I suppose. When we use the type object pattern instead, we replace an overridden method with a member variable. Instead of having monster subclasses that override a method to calculate an attack string using different code, we have a breed object that stores an attack string in a different variable. This makes it very easy to use type objects to define type-specific data, but hard to define type-specific behavior. If, for example, different breeds of monster needed to use different AI algorithms, using this pattern becomes more challenging. There are a couple ways we can get around this limitation. A simple solution is to have a fixed set of predefined behaviors, and then use data in the type object to simply select one of them. For example, let's say our monster AI will always be either stand still, chase hero, or whimper and cower in fear. Hey, they can't all be mighty dragons. We can define functions to implement each of those behaviors. Then we can associate an AI algorithm with a breed by having it store a pointer to the appropriate function. Sound familiar again? Now we're back to really implementing vtables in our type objects. Another more powerful solution is to actually support defining behavior completely in data. The interpreter and bytecode patterns both let us build objects that represent behavior. If we read in a data file and use that to create a data structure for one of these patterns, we've moved the behavior's definition completely out of code and into content. That's what I was thinking is maybe like a JSON object that you could then say like, here's what a troll is, here's its health, here's what it says, like for these specific two things, and then you can just loop through that and then create all the monsters you need dynamically. Over time, games are getting more data-driven. Hardware gets more powerful, and we find ourselves limited more by how much content we can author than how hard we can push the hardware. With a 64K cartridge, the challenge was cramming the gameplay into it. With a double-sided DVD, the challenge is filling it with gameplay. Scripting languages and other higher-level ways of defining game behavior can give us a much-needed productivity boost at the expense of less optimal runtime performance. Since hardware keeps getting better but our brain power doesn't, that trade-off starts to make more and more sense. All right, sample code time. For our first pass at an implementation, let's start simple and build the basic system described in the motivation section. We'll start with the breed class. Okay, so now we're gonna update. So if I rename this file, so like type object, what do we call this? So this was in the like behavior section. Now if I move on to, this is like the sample code. So let's go sample code.js. So now we're recreating and going into breed. Hello on Earth, good morning. Civilization has that computer power issue. It never, Civ 1 through 6 performed faster as they put more and more load on the engine. Yeah, I guess like because as they made for every new version, they of course tuned and made the engine better, but then they added more content to like cancel that off. So yeah, I mean, it makes a lot of sense. If you get faster, but you don't need to get faster because everybody's happy with the performance, then just add more things to take up the space. But then adding more things gets more interesting, so that make things easier to add. And that's how you get like all the religion system, the culture system, the ability to take over the cultures, heroes, much more complicated interactions between the science and technology and everything else, and you can't just run away anymore. And the AI system is more advanced, like all sorts of interesting things. But all right, let's do this. So we're gonna have our class breed. So we're gonna have a constructor on this that takes in the health and it takes in the attack string. So this dot health equals health. This dot attack string equals attack string. Then we're gonna have get health, which just returns health. So in JavaScript here, I would probably just say get health, return this dot health, and then get attack. So get attack string, return this dot attack string, and that's pretty much it for our breed. Yeah, more levels of complexity. Good stream, by the way. Oh, thank you very much. Hello. Very simple. It's basically just a container for two data fields, the starting health and the attack string. Let's see how monsters use it. Okay, so now we have our class monster. And so we're gonna have a constructor here, which takes in a reference to a breed. So this dot, okay, so then we're just gonna store the health from this. We're not gonna store the breed permanently, we're just gonna extract it right here. So this dot health equals breed dot health. Now in JavaScript, we don't need to do like the get or call it as a function because this getter actually makes it look like a property, sort of like a computed property in Vue. And then Interesting. So we're going to store the health. Oh, because this is the initial health. And then we're going to store the breed off. Okay. So this dot breed equals breed. Then we're going to have our get attack, which sounds like it's just going to follow that along. So we're going to do get attack. I'll just do attack string, which then just does, so in this case, there's no super, so it's going to be return this dot breed dot attack string. And there we go for that. When we construct a monster, we give a reference to a breed object. This defines the monster's breed instead of the subclasses we were previously using. In the constructor, monster uses the breed to determine its starting health. To get the attack string, the monster simply forwards the call to its breed. This very simple chunk of code is the core idea of the pattern. Everything from here on out is bonus. Okay, so that's actually really interesting. That means if we were to use this in like the setup, I guess, we would first create the breed. So const, what is the breed, like dragon? So we would have dragon equals new breed. We're going to pass in, what was it, like 248? 248 and the dragon breathes fire on you. So that sets up our breed, and now we're going to have the monster, which is the specific instance of this dragon. So then we can have const, we can name the dragon. So we can have, we'll have Sally the dragon. Sally dragon equals, it's going to be new monster. We're going to pass in a reference to the monsters. That's going to be the dragon. And that's it. So now at this point, we could do things like SallyDragon.attack string. So I think that's how we would end up using this. Making type objects more like types. Constructors. With what we have now, we construct a monster directly and are responsible for passing in its breed. This is a bit backwards from how regular objects are instantiated in most object-oriented programming languages. We don't usually allocate a blank chunk of memory and then give it its class. Instead, we call a constructor function on the class itself, and it's responsible for giving us a new instance. We can apply the same pattern to our type objects. Okay, so we have our class breed here. And we have a monster, which returns a new monster. Okay, so now we don't need this anymore. Or we don't need to like do this, essentially. So inside of breed here, and maybe above here, we're gonna have a method named new monster, which then returns a new monster, and then passes in this for the breed. Now I don't have to do anything like, using any special symbols because this is JavaScript. Any objects, and this would be an object, is automatically passed by reference. So in this case, we no longer need to do this anymore. Now we create Sally. So we have our dragon. So Sally Dragon is now going to be dragon dot new monster, like that. Pattern is the right word here. What we're talking about is one of the classic patterns from the design patterns factory method. Okay, that's what I thought at the beginning of this, is that this looked very similar to factory. In some languages, this pattern is applied for constructing all objects. In Ruby, Smalltalk, Objective-C, and other languages where classes are objects, you construct new instances by calling a method on the class object itself and the class that uses them. Okay, so monster, friend class breed. I don't know what that does in C++. But okay, so we're gonna still have get attack here. Return breed attack string. So we're still doing that. Yeah, what's different about this? There's like the friend class breed, which I don't think exists. Like that concept doesn't even exist in JavaScript from what I can tell. We have, oh, that replaces the constructor here. Interesting. That being said, I don't think we can apply this exactly like this. So we have get attack, return breed.getAttack. That's going to be very similar to this. Monster. So private, now we have a monster method on here. That takes in a breed, a reference to a breed. And then we're setting in, oh no, this is the constructor. This is I keep on forgetting that the construct, like there is no like constructor name. I really like this because it's so explicit. But okay, so our constructor takes in a breed, sets the health, and sets the breed. Exactly what we're doing before. We have get attack string, which still is right here, and that's pretty much it. There's not really any changes that we have to make to it. The key difference is the new monster function in breed, which is up here. That's our constructor factory method. With our original implementation, creating a monster looked like monster equals new monster some breed. After it changes, it's something like monster equals some breed dot new monster, which we show down here. There's another minor difference here. Because the sample code is in C++, we can use a handy little feature, friend classes. We've made monsters constructor private, which prevents anyone from calling it directly. Friend classes sidestep that restriction so breed can still access it. This means the only way to create monsters is by going through new monster. Hello, you Googled C++ friend functions. A friend function of a class is defined outside that class's scope, but it has the right to access all private and protected members of the class. Even though the prototype for the friend functions appear in the class definition, friends are not member functions. Oh, fascinating. So it's kind of like a way of doing inheritance, but only for the methods, not for the like private scoped, variable contents or the properties essentially, which is fascinating. It's not something we can do in JavaScript, but we can definitely, it almost doesn't matter. Like the way that we do this, we don't need the friend class. Probably because there's no such thing as like static versus protected versus anything else. It just exists. JavaScript lets us do anything. So why do this? There are two steps to creating an object: allocation and initialization. Monsters constructor lets us do all the initialization we need. In our example, that's only storing the breed, but a full game would be loading graphics, initializing the monster's AI, and doing other setup work. However, that all happens after allocation. We've already got a chunk of memory to put our monster into before its constructor is called. In games, we often want to control that aspect of object creation too. We'll typically use things like custom allocators or the object pull pattern to control where in memory our objects end up. Defining a constructor function in breed gives us a place to put that logic. instead of simply calling new, the new monster function can pull the memory from a pool or custom heap before passing control off to monster for initialization. By putting this logic inside breed, in the only function that has the ability to create monsters, we ensure that all monsters go through the memory management scheme we want. Thanks for translating. You're not good at C++. I've not used C++ myself, so it's definitely something that I'm learning as I'm going along. But yeah, I'm very happy to sort of like look through, and I think I have enough experience with C-based languages that I can sort of kind of see what's going on. But there's been a few times that I've been like, I don't know if I've got this right. Sharing data through inheritance. What we have so far is a perfectly serviceable type object system, but it's pretty basic. Our game will eventually have hundreds of different breeds, each with dozens of attributes. If a designer wants to tune all of the 30 different breeds of troll to make them a little stronger, she's got a lot of tedious data entry ahead of her. What would help is the ability to share attributes across multiple breeds in the same way that breeds lets us share attributes across multiple monsters. Just like we did with our original OOP solution, we can solve this using inheritance. Only this time, instead of using our language's inheritance mechanism, we'll implement it ourselves within our R-type objects. To keep things simple, we'll only support single inheritance. In the same way that a class can have a parent-based class, we'll allow a breed to have a parent breed. Okay, so we have now our breed here. So breed is going to take, before health, it's now going to take a parent. Then health, and then the attack string. So that means we have to store the parent here too. So this dot parent equals parent. So we have get health, get attack. That's all exactly the same. Well, there's nothing new about that. We're just storing the parent. I assume we're going to do something new with it in a new monster here. When we construct a breed, we give it a parent that it inherits from. We can pass in null for a base breed that has no ancestors. To make this useful, a child breed needs to control which attributes are inherited from its parent and which attributes it overrides and specifies itself. For our example system, we'll say that a breed overrides the monster's health by having a non-zero value and overrides the attack by having a non-null string. Otherwise, the attribute will be inherited from its parent. Okay, so we're going to check to see if the parent has a health or attack string. Interesting. Oh no, we're going to check if we are passed in a health or attack string. Oh, okay. So in get health here, if internal health, so is not equal to zero. Okay. Here's what I can do then. No, not that. Don't auto select for me. We're gonna set these to default to empty strings or empty zeros, like that. And this will allow us to. Now I understand we can do this at this point in time. But what I don't understand is why do it at this point in time? Why not do it here? So this is just in get health and get attack that we're updating here. So I'll do it the way they sort of like they're suggesting first, which is we're going to do a quick if check. So if this dot and you know, I could set this. I mean, it works. So if this dot health is 0. Okay, so if this health is 0. Then we're going to return this dot parent dot health. Otherwise, return this dot health. And we're going to do the exact same thing with the attack string here. So if this dot attack string, if that's equal to an empty string, then return this dot parent dot attack string. Now what are they doing here? So health, if health is not equal to 0, or the parent is null. What if you do if the health is 0 and the parent is null? That's a problem. Then I guess you have to like throw an error. Blackbird SLP, good morning. Is a web developer essentially a JavaScript developer these days? Yes. It's interesting. A web developer these days is somebody who has the ability to do anything web development related. So that's HTML, CSS, JavaScript. And more often, it's also full stack is required, or really nice. These days, like if you're going up in a interview position versus somebody who has full stack capabilities and you do not, you're probably not going to get the job compared to that full stack person, because they're going to get double the bang for the buck. So learning a little bit of backend, even if that's just JavaScript, a little bit of Node.js can go a long way in that. So yes, I would say that JavaScript developer is an essential part of web development. Quantum, good morning. Is this Bob Nystrom's book? It is. We are on chapter 13. Okay, so we're checking both of these to be null. And then we're like choosing to return which one we want to do. Now, I would almost do this up here instead, in the constructor. So like my idea would be, okay, we have, let's say I set this to be null, to be default. So it'd be easy for us to check to see if this health is not set. So we have this .parent, we're gonna store the parent away, and that's fine. And maybe we don't even need to store the parent at all. But it's actually free for us because we can store that. What's the difference between 0 and null? So 0 is just like the integer 0, so it's like the actual literal number 0. Null is just like nothing in programming. So I'm going to be able, that 0 and empty string would technically work, but it'd be very confusing for somebody looking at this. Undefined is also the other nothing. JavaScript has two nothings, null and undefined. Undefined is set automatically when something is not defined, and null, it can only be set by us humans. So I use null to sort of like as a way for me to like understand that it's me who said it. Okay, so I can set this here at this point. So this .health equals, and what I really want to do is check to see if not health, there's a few different things here. If not health, then take our parents. So then we'll do, if we don't have health, and this is interesting, if health is not equal to 0 and parent is null. Okay, so if we do that, so if health exists, now this is very interesting. We can just do this because JavaScript has this idea of truthiness as opposed to actually requiring the Boolean value truth. So if health is a truthy value, or parent, parent, so I can also set this to be null as well. So if parent is null, so if we have not parent, so if we have a health and we don't have a parent, then go ahead and set the this dot health equals to health. Otherwise, set us to the parent's health. So this dot health equals parent dot health. I guess it would be get health. I'll probably just do health. Something like that. And then we do the exact same thing to breed here. So then this goes away. We've now set health one way or the other. And we could do, okay, this dot if. Now I can see this. This is moving this sort of nasty if else into down here, which makes the constructor a little bit nicer to look at. Then we could do the exact same thing. So if attack string or but is it? Yeah, I guess so. If attack string or not parent, this dot attack string equals attack string. Else, this dot attack string equals parent dot attack string, like that. And now down here in health and attack string, now we can just do this entire return this dot attack string. So the get health becomes much simpler. All this happens up here. We can even do something where, hey, if all of them are null, throw an error at constructor time. That's an option. Will JavaScript become an even more important programming language in the near future? I mean, yes. I think it's just going to keep on getting more and more important as time goes on. Mainly because like we're moving more and more towards just web everywhere. Especially because if you want your app to run all over the place, it's a web app. And web apps are websites that just do a lot of stuff. Okay. This has the advantage of doing the right thing if a breed is modified at runtime to no longer override or no longer inherit some attribute. On the other hand, it takes a bit more memory. It has to retain a pointer to its parent. And it's slower. It has to walk the inheritance chain each time you look up an attribute, which is why I did this. It's not like it doesn't have to do that anymore. If we can rely on a breed's attributes not changing, a faster solution is to apply the inheritance at construction time. This is called copy down delegation because we copy inheritance attributes down to the drive type when it's created. Okay, I just walked ahead of it a little bit. He actually switches over and does this in the constructor right now. Note that we no longer need a field for the parent breed. Okay, yeah, so he no longer even stores this dot parent. Once the constructor is done, we can forget the parent since we've already copied off all of its attributes in. To access a breed's attribute, we now just return the field. Nice and fast. Let's say their game engine is set up to create the breeds by loading a JSON file that defines them. It could look like, all right, so if we take this and copy this into a JSON object, so this will be like, I guess breeds.json. like this. In our sample code, if we're running this in Node.js, it's pretty simple to bring this in. We just do const breed data equals require breeds to JSON. And that now we have that data, and we can see our IDE even understands it. We'd have a chunk of code that reads each breed entry and instantiates a new breed instance with its data. As you can see from the parent troll fields, the troll archer and troll wizard breeds inherit from the base troll breed. So we can see, okay, its parent is troll. So we're gonna have to have like a little bit of logic when we loop through this to then like figure out how to deal with it. Since both of them have 0 for their health, they'll inherit from the base troll breed instead. This means now our designer can tune the health in troll, and all 3 breeds will be updated. As the number of breeds and the number of different attributes each breed has increase, this can be a big time saver. Now with a pretty small chunk of code, we have an open-ended system that puts control in our designer's hands and makes the best use of their time. Meanwhile, we can get back to coding other features. I think the other thing is we can redesign this JSON to basically have like a parent section and then the like the children section, and then we can get rid of health on these ones. It will make it a little bit easier for us to loop through it. I don't know, like we'll have to sort of decide, like we might, I don't know, there's a couple different ways we can go about it. That might be like optimizing the data a little bit too much for the developer as opposed to the designer. We'd have to like work with the designer to see what makes sense for them. Okay, design decisions. The type object pattern lets us build a type system as if we were designing our own programming language. The design space is wide open, and we can do all sorts of interesting stuff. In practice, a few things curtail our fancy. Time and maintainability would discourage us from anything particularly complicated. More importantly, whatever type object system we design, our users, often non-programmers, will need to be able to easily understand it. The simpler we can make it, the more usable it will be. So what we'll cover here is the well-trodden design space, and we'll leave the far reaches for the academics and explorers. Is the type object encapsulated or exposed? In our sample implementation, Monster has a reference to a breed, but it doesn't publicly expose it. Outside code can get directly at the monster's breed. From the codebase's perspective, monsters are essentially typeless, and the fact that they have breeds is an implementation detail. We can easily change this and allow Monster to return its breed. Okay, so that would, so monster, so we have this new monster, return this, which then has breed. Does it have breed? I get, yeah, it does. That's stored here. So this means we have the get breed on here. So get breed, return this dot breed. As in other examples in this book, we're following a convention where we return objects by reference instead of pointer to indicate to users that null will never be returned. This is also something like, if we're doing this in Rust, we'd probably just return an option in case there wasn't a breed. But then if it isn't, then like there is no null in Rust. So like there's another way we can like say, hey, it will never be null. This whole topic is pretty irrelevant in JS because it's dynamic, and as such, you can just create actual dynamic classes at runtime. Absolutely, yes, definitely. Doing this changes the design of Monster. The fact that all monsters have breeds is now a publicly visible part of its API. There are benefits with either choice. If the type object is encapsulated, the complexity of the type object pattern is hidden from the rest of the codebase. it becomes an implementation detail that only the typed object has to worry about. The typed object can selectively override behavior from the typed object. Let's say we wanted to change the monster's attack string when it's near death. Since the attack string is always accessed through monster, we have a convenient place to put that code. Okay, so we now have monster get attack. If health is low, the monster flails weakly. So interesting. Okay, so now this attack screen can be like multiple things. So if this dot health is less than like whatever some like defined, so we can have a const up here. Low health equals this usually might be something like 25%. So if I do something like 0.25, then we multiply that. Maybe just for this one, I'll just follow the same pattern. We'll just say something like 10. If it's below 10. So attack string, if it's below low health, then we're going to return the monster flails weakly. Otherwise, return this .breed .attack string. If outside code was calling get attack directly on the breed, we wouldn't have the opportunity to insert that logic. We have to write forwarding methods for everything the type object exposes. This is the tedious part of the design. If our type object class has a large number of methods, the object class will have to have its own methods for each of the ones that we want to be publicly visible. If the type object is exposed, outside code can interact with type objects without having an instance of the typed class. If the type object is encapsulated, there's no way to use it without also having a typed object that wraps it. This prevents us, for example, from using our constructor pattern where new monsters are created by calling a method on the breed. If users can't get to the breeds directly, they wouldn't be able to call it. The type object is now part of the object's public API. In general, narrow interfaces are easier to maintain than wide ones. The less you expose to the rest of the codebase, the less complexity and maintenance you have to deal with. By exposing the type object, we widened the object's API to include everything the type object provides. How are typed objects created? With this pattern, each object is now a pair of objects, the main object and the type object it uses. So how do we create and bind the two together? Construct the object and pass in the type object. Outside code can control allocation. Since the calling code is constructing both objects itself, it can control where in memory that occurs. If we want our objects to be usable in a variety of different memory scenarios, different allocators on the stack, etc., this gives us the flexibility to do that. Call a constructor function on the type object. The type object controls memory allocation. This is the other side of the coin. If we don't want users to control where in memory our objects are created, requiring them to go through a factory method on the type objects gives us control over that. This can be useful if we want to ensure all of our objects come from a certain object pool or other memory allocator. Can the type change? So far, we've presumed that once an object is created and bound to its type object, that the binding will never change. The type an object is created with is the type it dies with. This isn't strictly necessary. We could allow an object to change its type over time. Let's look back at our example. When a monster dies, the designers tell us sometimes they want its corpse to become a reanimated zombie. We could implement this by spawning a new monster with a zombie breed when a monster dies, but another option is to simply get the existing monster and change its breed to a zombie one. Oh, that's fascinating. Okay. So for example, when Sally Dragon dies, because the monster has a breed that's stored, we could then like have a set on here. It's like we can have a set for the breed that would take in a new breed, and then do this dot breed equals breed, something like that. So then Sally Dragon dot breed equals, I guess it would be like zombie dragon. So then we'd have const zombie dragon equals new breed. And it's going to be something like, maybe it only has 100 health, and the zombie dragon lurches at you. That's fascinating. So that allows us to sort of like just say, okay, now you're a zombie dragon. If the type doesn't change, it's simpler both to code and to understand. At a conceptual level, type is something most people probably will not expect to change. This codifies that assumption. It's easier to debug. If we're trying to track down a bug where a monster gets into some weird state, it simplifies our job if we can take it for granted that the breed we're looking at now is the breed the monster always had. Of course, if we're in something like JavaScript where, types are willy-nilly, then we're just already in the mindset that we don't know what we're looking at. If the type can change, there's less object creation. In our example, if the type can't change, we'll be forced to burn CPU cycles, creating a new zombie monster, copying over any attributes from the original monster that needed to be preserved, and then deleting it. If we can change the type, all that work gets replaced by a simple assignment. We need to be careful that assumptions are met. There's a fairly tight coupling between an object and its type. For example, a breed might assume that a monster's current health is never above the starting health that comes from the breed. If we allow the breed to change, we need to make sure that the new type's requirements are met by the existing object. When we change the type, we will probably need to execute some validation code to make sure the object is now in a state that makes sense for the new type. What kind of inheritance is supported? No inheritance. It's simple. Simplest is often best. If you don't have a ton of data that needs sharing between your type objects, why make things hard on yourself? It can lead to duplicated effort. I've yet to see an authoring system where designers didn't want some kind of inheritance. When you've got 50 different kinds of elves, having to tune their health by changing the same number in 50 different places sucks. Single inheritance. It's still relatively simple. It's easy to implement, but more importantly, it's also pretty easy to understand. If non-technical users are going to be working with the system, the fewer moving parts, the better. There's a reason a lot of programming languages only support single inheritance. It seems to be a sweet spot between power and simplicity. Looking up attributes is slower. To get a given piece of data from a type object, we might need to walk up the inheritance chain to find the type that ultimately decides the value. If we're in performance critical mode, we may not want to spend time on this. Multiple inheritance. Almost all data duplication can be avoided. With a good multiple inheritance system, users can build a hierarchy for their type objects that has almost no redundancy. When it comes time to tune members, we can avoid a lot of copy and paste. It's complex. Unfortunately, the benefits for this seem to be more theoretical than practical. Multiple inheritance is hard to understand and reason about. If our zombie dragon type inherits both from zombie and dragon, which attributes come from zombie and which come from dragon? In order to use the system, users will need to understand how the inheritance graph is traversed and have the foresight to design an intelligent hierarchy. Most C++ coding standards I see today tend to ban multiple inheritance, and Java and C# lack it completely. That's an acknowledgement of a sad fact. It's so hard to get it right that it's often best to not use it at all. While it's worth thinking about, it's rare that you want to use multiple inheritance for the type objects in your games. As always, simpler is better. And then we have some C alsos. So like a high level problem. Okay, so like the prototype pattern is one way to solve this. Then there's the flyweight pattern, which we already looked at in a previous video. And this sort of like reminds me of that, specifically with this this breeds here. There's a lot of similarity with the state pattern. Both patterns let an object delegate part of what defines itself to another object. When we discussed having an object change its type, we can look at that as having our type object serve double duty as a state too. Something else that we could do potentially here is we could have a troll here. Troll here, has its attack health 25. We have troll archer have its parent be a troll. We can have a compiler for this JSON that creates another JSON that then sets essentially removes the parent and has its health now be 25. This allows us to have our designers sort of update this document. Then we run a compiler that creates all of this. Then in our code, we don't have to worry about figuring out like the parents or anything else. We have a 1-2 step for getting in there. I would probably also change this to be an array. Although what I might do before I do that, let's say I do this as like parents. So if I have like parents, I just want to see what this looks like. Now we move troll into parents. Then we have children. Should make this lowercase. Now these can be an array. Is that true? No, we don't want them to be array. Still, we can look up through this. Children are now in here. Still don't need it to be an array. Now we could say, okay, parent is troll, so it's referencing it's referencing this. But when I go to use this, it's going to be easy because I can say, okay, when I loop through all of these children, I can now dynamically create our objects. And I can say, it's going to be upset at me because I'll just in a comment. Let's say I get a child through some kind of loop. Like I'm looping through all of the children. I get the parent. And so now I can say the breed dot health equals parents of breed dot parent dot health, essentially like that. Oh no, it's gonna be parents breed dot parent dot health, like that. So it's a lookup table now, where we don't have to like do another loop through or anything to find it. We just go straight to it, which is super fast. And this is part of like our potential second compiler, or just as we're looping through all the children, we don't have to ever loop through the parents ever, because we just know parents can't be hit. Like parents don't create anything, which this is something that would be super interesting to try out. I also am thinking about trying to like create the base of this pattern in Rust. Because there's no inheritance, we can do that. But I would have to do that tomorrow. Because it is 8:15, which means I have to run and start getting ready for my stand-up and my day. It's the end of our sprint, so a lot of sprint meetings and plannings and all sorts of fun stuff. Plus, I'm planning on doing a deploy today, so it's gonna be interesting at work. But let me go ahead. I'm gonna switch over to the ending screen. Thank you everybody for stopping by and watching this. I've been going through and reading this book just for my own learning, but I also like to do this on stream. First of all, because it just gives me a little bit of a reason to do it in the morning before work. But also, I find that I slow down when I explain things. I get a lot out of it. I'm hoping that you're getting a lot out of it as well. I'm doing these streams every weekday morning at 7 a.m. Mountain Time. And tomorrow, I think I'm going to do this pattern in Rust. Just sort of like what I have here, the sample stuff. And then we'll sort of like figure that out. If we get done with that early, then we'll start reading through the next pattern. Anyways, thank you again for stopping by. I hope that you all have a great rest of your day if it's beginning, or a great night if it's ending. And with that, have a great day, and I'll see you next time.